Question 3.60. Three charges Q1, Q2 and Q3 are located at the corners of an equilateral triangle with side of length 1.20 meter. Find the work done in each of the following cases. So here in this question you have 3-point charges Q1, Q2, Q3 which are placed at each corner of an equilateral triangle. And we need to find the work done in bringing each of them in their respective position. So let us start with part A. In part A, we need to find the work done to bring the first particle Q1, which has a charge of 1 picocoulomb, to P from infinity. So first, if we only bring charge Q1 from infinity to point P, Q1 has no other charge to interact with. So work done in bringing Q1 from infinity to this point over here will be equal to 0, as the point is an empty space and there is no other charge that Q1 has to interact with. So I can write W1 to be the work done in bringing charge Q1 to be equal to 0 joule. Next in part B, we bring the second particle Q2, which has a charge of 2 picocoulomb, to Q from infinity. Now when you bring charge Q2 from infinity to point Q, you have to do work against charge Q1. So we can write work done in bringing charge Q2 as W2 to be equal to K Q1 Q2 over R. And this work has to be done because of the interaction between Q1 and Q2. And R is the distance between them. For us, it is equal to L. So we can write K as 9 times 10 to the power 9. Q1 is 1 picocoulomb. So pico has a power of 10 to the power negative 12. So we write as 1 times 10 to the power negative 12. Q2 is 2 picocoulomb. So 2 times 10 to the power negative 12 over the distance between them, which is L. And L is equal to 1.20 meter. Substitute that here, 1.20. And when you solve this, you get work done W2 to be equal to 1.498 times 10 to the power negative 14 joule, which you can round off to 1.50 times 10 to the power negative 14 joule. So this is the work done in bringing charge Q2 from infinity to point Q. Then in part C, we need to bring the last particle Q3, which has a charge of 3 picocoulomb, to R from infinity. So now we're bringing the third charge particle at point R. And in order to bring this third charge, you have to do work against charge Q1 and Q2 to place Q3 at point R. So work done in bringing the third charge W3 will be work done against Q1 and Q2. So we write K Q1 Q3 over R13 plus K Q2 Q3 over R23, where R13 is the distance between charge 1 and charge 3, which is equal to L, and R23 is the distance between charge 2 and charge 3, which is also equal to L. Now let's take the common term outside here. K and Q3 are common for both, so we write K Q3. R13 and R23 both are equal to L, so we can keep this also outside. Then we are left with Q1 plus Q2. Now substitute their values. We get W3 to be equal to K is 9 times 10 to the power 9. Q3 is 3 picocoulomb. So 3 times 10 to the power negative 12. Q1 and Q2 both are measured in picocoulomb. So their powers, I can take it outside as common term. So we will multiply with 10 to the power negative 12 again. Q1 is 1, Q2 is 2 over the distance L is 1.20. And when you solve this, You get the work done in bringing the third charge particle to be equal to 6.743 times 10 to the power negative 14 joule, which you can round off to 6.74 times 10 to the power negative 14 joule. So this is the work done in bringing the third charge at its position. In the last part of the question, they want you to find the total potential energy stored in the final configuration of Q1, Q2, and Q3. Now, when we bring charge Q1, Q2, and Q3 at their respective position, we have to do work against the interaction between the charge. And this work done is stored as the potential energy of the system. So my total potential energy U of the system will be equal to sum of all the work done in assembling these charges in the given configuration. That will be equal to W1 plus W2 plus W3, which is equal to W1 is 0, W2 is 1.50 times 10 to the power negative 14, plus W3 is 6.74 times 10 to the power negative 14. And when you add them, you get the total potential energy of the system to be equal to 8.24 times 10 to the power negative 14 joule.